Good afternoon, dear students. Today we will take some examples, illustrate the concepts of chromatographic separation mechanisms. So, if you remember, we cover the main mechanisms, namely size exclusion mechanism and partitioning, as well as adsorption. And we shouldn't also forget ion exchange mechanism, either cation exchange or anionic exchange. Today we will take some examples and we will think which mechanisms might be more suitable for separating this group of compounds, and how can we apply it. Now, for example, if we have now this is catechol, as you know from organic chemistry. This is catechol, which is orthohydroxyphenol. This is hydroquinone, which is bleaching agent and used in some creams like Fair and Lovely cream. And the last one is resorcinol. Now, resorcinol is metahydroxyphenol. Now, all of them have the same functionalities. Okay, 2-hydroxy with benzene ring. In terms of partitioning, there's no big difference among them. However, the main difference in intermolecular hydrogen bonding, or the interaction with other entities. Now, orthohydroxyphenol is busy with intramolecular forces. So there's a trivial chance for it to make hydrogen bonding with silanol. Okay? Now, parahydroxyphenol, which is hydroquinone, it can make good bonds because we can anchor it from the right-handed functionality and the left-handed functionality. Okay, so it can use both of the functionalities. Okay, now the resorcinol, which is metahydroxy, still can do hydrogen bonding. If you remember from organic chemistry that the molecule which has the highest boiling point is hydroquinone, and the reason that it has strong intermolecular hydrogen bonding due to the availability of 2-hydroxy group for intermolecular hydrogen bonding. There is no chance for them to make bond through the molecule, intramolecular bonds. They are completely opposite. Okay, we have almost 180-degree difference between these two functionalities. Okay, so this one has the highest boiling point, and catechol has the least boiling point. So it's busy with intramolecular hydrogen bonding, and its capability to form hydrogen bond with silica is less. So the adherence of hydroquinone should be more than the others, and for catechol should be the least one which can adhere with silica. So we will choose normal phase silica. Obviously, normal phase silica has an advantage of differentiate these compounds according to their ability to form intermolecular bonds, particularly physical bonds. We are talking just about physical bonds, which are reversible bonds. Now, we can think of size exclusion, but the difference in molecular weight is zero. Okay? Now, in order to have size exclusion contribution, we have to have substantial difference between the entities in terms of molecular weight. For example, when we are talking of phenol, the other one should be, for example, protein, or should possess at least 3 or 5 times molecular weight of phenol in order to be easily differentiated in size exclusion dependent chromatography. Uh, you might think of cationic exchange. Cationic exchange. Uh, do we have cationic capability here in these compounds? Can these compounds bear cations? Obviously, this is impossible. We can also think of anionic exchange. Can these functionality carry anionic ions? Yes, they can. For example, this kind of phenols, if we increase pH of the mobile phase above 10, then these compounds can take ions. Okay. The problem that in chemistry that the first ionization is much stronger than the second ionization. So we might just in pH just above 10, like 11, we might only ionize one of them. Okay. If we are talking about silica-based ion exchange, what do we mean? If we have silica and we modify silica to have positive charge by some compounds. We have silanol, then we add certain compounds to silica in order to possess positive charge. Now, silica can act as what? Can act as a surface of anion exchange. The problem that pH of the silica shouldn't exceed 8, from 2 to 8. So if we want to get phenol ionized, it has a pKa of 10 and it is acid. So in order to ionize acid, which has a pKa of 10, we have to increase pH at least with 1 unit. If we put the pH around 10, it will be 50% ionized. If we increase pH to be 11, then mathematically, according to Henderson-Hasselbalch equation, 90% of the molecules will be ionized. Now, all the time, pKa1 of the molecule must be better in term, depends on the acidity or basicity, must be better than the second pKa. So the compound will be easily ionized according to the first pKa, but it's difficult to be ionized by the second pKa. For example, pKa of catechol, the first pKa might be 10, the second pKa might be 20. I don't know exactly, but it should be much higher. Much higher means weak acid, very, very weak acid, the second one. Okay. So we cannot increase pH of the mobile phase above 8. So there is no chance to rely on silica-based anionic exchange chromatography. Now we have alternative, as I mentioned previously, that some of the ion exchange chromatographic systems, stationary phases, rely on polymers. such as polystyrene cross-linked with divinyl benzene. So it is robust, tolerant. It is tolerant against extreme pH values. Accordingly, we have polymeric-based stationary phase. It can tolerate. This is polymer tolerates wide range of pH from 1 to 14, for example. So we can increase pH above 11 in order to get these molecules ionized. But the problem, all of them will be monovalent, just one charge. So again, there is no chance, even by using an ionic exchange, to get these compounds separated. You may see that I might use very strong base in mobile phase in order to get the second ionization, even if you very strong base, which is applicable in application unacceptable. You will get all of the compound the same charge, divalent. So there is no real differentiation between or among these compounds. Now, so the only method for the example and for the compounds in the example is normal phase chromatography, and this can be done by using simply silica, and the mobile phase should be hydrophobic, such as hexane, chloroform, methanol with chloroform, methanol with hexane. So it depends on the system and its capability to separate compounds. Okay, but the majority or the main character of the mobile phase sorry, should be oily in order to get not completely oily, because we need competition. That's why we add methanol or acetonitrile to chloroform or to hexane in order to make it a little bit competitive to the stationary phase. Now it's easy to see that there is no chance for ion exchange. Okay, we have ketone here, we have benzene, we have here phenyl with two big alkyl moieties. Now there is no chance for ion exchange. There is no chance for normal phase because there is no functionality capable to form to form physical interaction with stationary phase, and the same thing for benzene. You might say we have chance for by stacking or induced dipole interaction, but this, these will be equivalent for two these molecules. Just benzene might contribute in such interaction, and this interaction practically negligible in chromatography. Here we have dipole moments, so we can form some interaction via oxygen atom. It has partially negative charge. But again, silica cannot be applied due to the lack of bond functionalities in all compounds. But obviously, uh, these two molecules are close in molecular weight, although this molecule has the this molecule has uh, real difference in molecular weight, we cannot apply again size exclusion. If we have just these two, we might apply size exclusion, particularly by using suitable pore size. Okay, but with this one, it is difficult to get all the compounds separated. So the unique mechanism is partitioning. Now, partitioning according to the lipophilicity, to the log P. Now, which is more hydrophobic? This one is the most hydrophobic one. And which one is the least hydrophobic? Is the one with carbonate, the least. So the one which has this one, which has the least interaction with stationary phase, will elute first. Then benzene, and the last one will be the most hydrophobic, which retain longer in hydrophobic stationary phase, such as ODS or C8. Okay. Now, if we have protein and we have a drug like this one, okay. Now, how can we separate these two compounds? Now, this is a protein, for example, with molecular weight 5 kilodalton. 5 kilodalton. And this is simply should be around 100 dalton, more or less. Okay, so 5 kilodalton, this means that we deal with what? With large, massive compound, whereas the drug has a small molecular weight. So in order to get these compounds separated, we apply in this case size exclusion, that the large compound will elute first due to intermolecular pathway passage, whereas the smallest molecule will take longer time due to the time consumed in passing both inter and intra particulate pathways. Okay. Now, which kind of mechanisms we can get these compounds separated? Uh, Obviously, normal phase absorption mechanism of normal phase will be applicable. So absorption, we can use absorption, that this compound can make two bonds. This compound can make one bond with silica. This compound can make no bond. So the The one which has number 1, this is 2, this is 3. The compound which has number 1 will go first, and the last one will be number 3. Okay, this is about adsorption mechanism. Now, size exclusion, there is no big difference, particularly between 1 and 2 in terms of molecular weight, so it is not applicable here. And thirdly, ion exchange. Ion exchange, yes. Ion exchange, these functionalities are far from each other. So they have the compound pKa will not be the first pKa will not be affected by second pKa, or second pKa not affected by first pKa. If the group are very close to each other, one of them will be ionized much more the other one. The other one will has weak pKa. But if they are far from each other, then each one will behave separately. So in neutral pH, amine has a pKa of what? Of around 9. Okay, like ammonia. So in a neutral pH, both will be amine will be what? Ionized. So both functionalities here at a neutral pH, at any pH, at pH 9, it will be 50% ionized. At pH 8, it will be 90% ionized. At pH 7, it will be almost, because log function we cannot reach 100%. At pH 7 will be almost 100% ionized. Any pH below 7, it also will be the same, 100% ionized. So we can get this compound ionized in any pH 8 and below. And this compound will has one positive charge. This compound will be in neutral. So if we use cationic exchange, okay, even silica-based cationic exchange, we can get this compound separated at a neutral pH or acidic pH, mobile phase. Compound 1 will elute first, and the least one, or the last one in elution, will be compound 3. Okay. And also partitioning mechanism will work, because when we have two amine, this will affect log P. When we have one amine, and the last scenario when we have no amine. So these three compounds, they have difference in terms of log P, and we can still apply a partitioning mechanism. Okay, and this is the end of the chromatographic mechanisms.